Hello, ladies and gentlemen. Root Beer here with question number 4 on the 2003 scholarship paper. That's the Euclid from the year 2003. That's the grade 12 level math contest. And question 4 has 2 parts, so let's get our pen ready. Part A here is just a light bulb question. And then we're going to have a written question where we have to do our explanation for part B. So question A. In a short track speed skating event, there are 5 finalists, including 2 Canadians. The first 3 skaters to finish win a medal. If all finalists have the same chance of finishing in any position, what is the probability that neither Canadian wins a medal? Okay. So the first thing I notice is that it's saying all the finalists have the same chance of finishing in any position. So that's what's called an equiprobable event. Everything has the same outcome. It's not like, say, there's a Soviet speed skater and they're twice as likely to place over anyone else. We don't need to factor that in any meaningful way. What we can do with an equiprobable event is we can count up the number of outcomes that we are looking at, the number that we are interested in. That is the number where no Canadian wins a medal. And we can divide that by the total number of possible outcomes. All the different ways that we can arrange the 5 finalist skaters in any order. So gold, silver, bronze, 4th, and 5th. Okay? So, with an equiprobable event, we're all set. We can just go ahead and jump right in there. And we can write down a tiny little formula for our probability. Oh, still on blue. So our probability is number of outcomes we want over the number of outcomes possible, the number of possible different ways to arrange all these finalists. That's the beauty of an equiprobable event. If it wasn't, if they hadn't said everyone has the same chance, we'd have to do other things to calculate this probability. And then it probably wouldn't be one of the little light bulb questions. It would probably be a little more involved. So we pick whichever one we want. Outcomes possible is the first one I'm going to do. So the number of outcomes possible that's just the number of ways to arrange our finalists, going from 1st all the way down to 5th. Okay? We're not given any extra conditions. We're not saying out of all the ones where the American gets gold or anything like that. We just have all our 5 finalists, and we arrange them 1st, 2nd, 3rd. That's gold, silver, bronze, and then 4th and 5th. So we don't care. We don't care about where the Canadians place right now. And the key word here is arrange. And when I'm talking about arrangements, we think factorial. So we got 5 things to arrange. 5 factorial. It's 5 times 4 times 3 times 2 times 1. Factorial is something you should have seen before, but if you haven't, here's a little crash course in it. And that's going to be 120. You can either know that because you have a bunch of experience with factorials. For example, offhand, I know all the way up to 7 factorial, which is 5,040, but beyond that, I probably need my calculator. Yeah, you should know a couple of these. 120 pops up a whole lot. So there are 120 ways for the race to be, run. Okay? We could have the American, the Soviet, one of the Canadians, a Brazilian, and then the second Canadian. Or we could have the first Canadian, the American, the second Canadian, the Soviet, and the Brazilian. Or the second Canadian and the American, the Soviet, the first Canadian, and the Brazilian. We could have all these possibilities. 120 of them, we're not going to list them out. Okay? Now, if you were having trouble figuring this out, and, that's possible. If you're having trouble figuring that out, and you say to yourself, well, I've looked at the other questions, I don't think I'm going to get 5, 6, any of them, you probably would have time to list out 120 of them. Just remember that your 2 Canadians are distinct, and then if you do list them all out, you can then really easily go look through and say, okay, that's one of the ones where no Canadian won a medal. That's one of the ones where no Canadian won a medal. And that makes the second half of this question, adding up the number of outcomes that we're looking at, the number of outcomes that we're interested in, where no Canadian wins a medal, that would make that a lot easier. But we're going to go through it a little quicker. So, that's the number of possible outcomes. Now for the number of outcomes we want. We don't have a list of all 120, so we can't just be checking them off and counting those up. So, where no Canadian wins a medal. So we're going to have to be a little clever about this. If no Canadian wins a medal, that means both Canadians, well, one Canadian gets 4th, and the other gets 5th. Okay? And the 3 other skaters, the non-Canadian skaters, I said American, Soviet, and Brazilian, but they don't give us nationalities, so I was just picking them off the top of my head. The 3 other skaters get medals. So they finish 1st, 2nd, and 3rd. Gold, silver, and bronze. So, to do this question, to answer how many ways can Canadians not win a medal, we have to figure out the number of ways that one Canadian can get 4th, the other Canadian can get 5th, and then the number of ways that the other skaters can finish gold, silver, and bronze. So we've got 3 other skaters, 3 non-Canadian skaters, and one of them needs to get gold, one of them needs to get silver, one of them needs to get bronze. Okay? So how many ways can we arrange these 3 other skaters to get gold, silver, and bronze? And there's that word arrange again. So once again, it's permutations, and we think factorial. We have 3 other skaters. We need to arrange them. That's 3 factorial. Oops. Wrong thing. I want the next page. So we need to arrange our 3 other skaters. And that's 3 factorial, which is 3 times 2 times 1. 6 different ways we can arrange those other skaters. And as for our 2 Canadians, we have to arrange them as well. One of them needs to get 4th, one of them needs to get 5th. And that's 2 factorial. Anytime you're just blanketly arranging things with no extra conditions, it comes down to factorials. We have 2 choices for the Canadian who gets 4th, and that leaves us with 1 Canadian left to choose to get 5th. We have 3 choices for the other skater to get gold, then there's 2 left over, because one of them got gold, 2 left over for our choice of who got silver, and 1 choice left over for the guy who gets bronze. The guy who's left over has to get bronze. So that tells us that there are 6 times 2, which equals 12. Combining these 2 different possibilities, the arrangement of the other skaters has nothing to do with our arrangement of the Canadians. So there are 12 ways for no Canadian to get a medal. And now our probability, as we already said, is just the number of outcomes we're searching for, the 12. The 12 where no Canadian gets a medal, and then the 5 factorial, the 120, which is just all possibilities. And that's 1 out of 10. That 10 there kind of looks like 5 choose 2. There's probably a nicer way to do this question. Yeah, you need to choose 2 people to not place. The number of ways to do that would be 5 choose 2, and that's 10, so 1 out of 10 chances for the Canadians. That's another sort of really quick verbal way to do the question. Okay, so that was A part. We got our answer, probability of 1 over 10. We don't actually need to explain or show my work. Alright, B part. This is the one where we need to justify. Determine the number of positive integers less than or equal to 300 that are multiples of 3 or 5, but not multiples of 10 or 15. Ooh, okay. So, we want to include some things, multiples of 3 and 5, but exclude others, the ones that are multiples of 10 or 15. So, to me, that immediately springs to mind the concept of the principle of inclusion and exclusion. And that's a way to count things very carefully so you get the right number. So what we're going to do is we're going to count up all the multiples of 3 that are less than 300. And add on to that all the multiples of 5 that are less than 300. Now, some of that will overlap. For example, multiples of 15 will be in both of those groups. So we'll have to figure out the number of multiples of 15 less than 300 and subtract those off, because we don't want to include those. We're excluding them. Okay? So, our plan of attack is number of multiples of 3 plus the number of multiples of 5, because that will definitely include everything that we want, but it's also going to have extras. And then in this list, we'll have multiples of 15. We don't want those. And in the multiples of 5, we're going to have multiples of 15. And then what should we do with the multiples of 10? Well, they're only going to be in the multiple of 15 list. The multiple of 5 list. So we're going to need to get rid of multiples of 10 here. But there are some multiples of 15 that are also multiples of 10. So we've sort of overlapped these two. When we take out our multiples of 10, we're almost taking out too much. Okay? So actually, here's a good example of that. So if I just did up to 30, our multiples of 3 are 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. That's our multiple of 3 list. I'll color code this a little bit. And then our multiple of 5 list, which we'll put down here. We have 5, 10, 15, 20, 25, 30. Now, in the blue list, the multiples of 3 list, we have some multiples of 15 that we don't want. And in the red list, we have some multiples of 15 that we don't want. Okay? But we've also got some multiples of 10 that we don't want. And when we go to remove all the multiples of 10, suddenly we've removed all our multiples of 30 twice. So we're going to have to add back in our multiples of 30, and I suspect that this is why this is a bit of a written question. Okay? Because there's some extra stuff, and we need to justify why do we add in the multiples of 30. Okay. So, let's count the number of multiples of 3 less than, what was it? 300. Less than or equal to? Less than or equal to. Okay, good. So the nice thing about that is we can just say it's 300 divided by 3. Every third one is a multiple of 3. So there are 100 multiples of 3 less than 300. Okay? But some of these are multiples of 15, which we don't want. So, of these 100, every fifth one Because to get a multiple of 15, it has to be 3 times 5. Just like every third number from 1 to 300 is a multiple of 3, in this list, every fifth one will be a multiple of 5. So right now in our list we have 100, the 100 multiples of 3 minus the 20 multiples of 15. What about multiples of 10? Any multiple of 10 in our list of multiples of 3. So here I'm explaining why I don't have to do anything with multiples of 10, and this is part of getting full marks. I have to explain my reasoning. So any multiple of 10 that was in our list of multiples of 3 was a multiple of 3 times 10, which is 30, and so was removed with the multiples of 15. So we already got rid of every multiple of 10 that was in our list. 30, 60, 90. These are the ones in the list. So right now, we are looking at, for our list of multiples of 3, we've got 80. Okay? So the answer is at least 80. Now, we might add some more that are multiples of 5 and not multiples of 15 or 10. For example, 5. So it's at least 81. Okay. So, now, let's count our multiples of 5 that are less than or equal to 300. Okay? Once again, every fifth one will do just fine. So 300 divided by 5 is 60. We've got 60 multiples of 5. Now some of these are multiples of 15. In fact, every third one. So we want to remove a third of these. It's 20 again. Oh, that makes sense. There's 20 multiples of 15 because 300 divided by 15, so there should be 20 in both lists. So we got 60 minus 20 equals 40. Now let's be really clear. Some in our list of 60 are multiples of 10. Every 10th one. No, sorry, every second one. Because they're multiples of 5, so you'll have 5, then you'll have 10. Then you'll have 15, then you'll have 20. So every second one. So we want to remove 60 over 2, half of them. Okay, so we'll have 40 minus 30 is equal to 10. But some of these multiples of 10 were already removed because they are also multiples of 15. So they were removed over here when we took out 20 multiples of 15. Now, since they were removed twice, we must add them back in. We tried to remove a 30, but 30 was already gone. So we still subtracted 1 off for that 30, but it was already removed. So we sort of have to add 1 back to correct for our mistake. And this is what the principle of inclusion and exclusion does. And it's a way of, I've mentioned it, this principle of inclusion and exclusion. All it does is sort of a way for you mentally to arrange these things in, I have to take out all of these and all of these. But I have to add back in anything that I've taken out twice. And then if I had a third set, I've taken out those, then I have to add in the overlap between these and these. And then I have to remove again anything that I've double added back in, and it's probably best explained with Venn diagrams almost. Actually, let's see if I can just digress for a moment and talk about this. So say I've got some Venn diagrams. Okay, maybe this blue is multiples of 3. Red's multiples of 5, and maybe we were doing an extra question where it's multiples of 2. Okay? So if we wanted to count up all the multiples of 2, 3, and 5 that are less than, say, 300, but not any of the multiples of 6, which are over here, not any of the multiples of 15, which are here, and not any of the multiples of 10, which are represented here, the overlap between the green and the red, we would need to take the blue number, add on the green number, add on the red number, subtract the numbers from these overlaps, and then, since this, the very middle, which overlaps with all 3 of them, has been subtracted off 1, 2, 3 times, we'd have to add 2 copies of him back on. Okay? Because otherwise we're removing extra numbers, we're removing 30s and 60s, several times, and we can only remove 30 from our list once. So that's the idea. So if you need to set up your principle of inclusion and exclusion, you could probably sit down and try and do it with a Venn diagram. Alright, so any multiple of 10 and 15 is a multiple of 30. Now we had a list of 60 multiples of 5. So every 6th one is a multiple of 30. So we had 60 minus 20 was 40, 40 minus 30 was 10, so we're at 10 plus adding back in the extra copies of multiples of 30 that we mistakenly took out when they weren't even there, we get 20. So these are the multiples of 5 that are not multiples of 10 or 15. So we have 80, that's the multiples of 30 that aren't multiples of 10 or 15. Plus the multiples of 5 that aren't multiples of 15 or 10. And that should give us a total of 100. Okay? And we've explained it at each step. We explained what we were doing. We even had a little sketch at the start of I was going to do multiples of 3 minus multiples of 15 and so on. But I explained it at each step. I said, here's our list of multiples of 3. Some of them are multiples of 15, so I'm removing those. There are none that I have, there are no multiples of 10 left in the original list that weren't already removed. Then I said, here are all the multiples of 5. We need to remove multiples of 15 and some multiples of 10, but oh no, some of the numbers have been removed twice. Those are the multiples of 30, so we add that number back on. Otherwise, we've improperly counted, and that got us our 100. So we've explained what's happened at each step of the way, and that's what we need to do for the written style questions. So that was question number 4. Join me for question number 5 in the next video, and I'll see you guys then.